I will introduce myself. I'm Andrea Gatti. I'm working for a small company located north of Milan. It's called GeoGuard. We are born in 2012 as a spin-off of Polytechnic of Milan under the supervisor of a professor of Polytechnico. And our main studies are related with geodetic data analysis. We are working in the field of gravimetric data analysis and GNSS deformation monitoring. So in the previous presenter showed you that it's very important to monitoring structures like a bridge. And here we are presenting a service for monitoring structure in a different way. It's a complementary technology. It's not a substitute, obviously. And we are using global navigation positioning system, such as GPS, Galileo, Beidou, whatever you want for different countries, to assess the position of a certain point with millimeter accuracy on daily solution or some millimeters for hourly solutions. GeoGuard is a service that can be used for monitoring different kinds of structure, such as building or bridges, but also landslides or reservoirs. And we have already done a lot of installation in different kind of structures, for different kind of monitoring of structures. So the system is based on relative positioning. We install a certain number of receivers on the sites that we have to monitor, and we compute relative position from one point to all the others, or other kind of combination. It's not required to have the visibility, the intervisibility between points, but we need obviously sky visibility to get satellite information. The data from the station are sent through internet or other kind of wireless system to the cloud. In the cloud, we compute solutions and we provide to the customer the information about the position of these points. Every site and every unit is calibrated and tailored specific for that kind of installation. So we provide the system as a service, and we are continuously improving our algorithm and our analysis. We start from doing the inspection on the site, and together with the client we decide how many points are needed, where to locate them, and we arrive to follow the client till the full customization of the installation. So we can also integrate other kind of instruments and sensors to our unit to provide data to the final client. This is, well, relatively too complicated scheme of the unit, but basically it's a GNSS module together with the processing unit that can be attached to other external sensor, such as temperature, pressure, or accelerometer, or whatever else. And they can be installed as standalone unit, so together with solar panel and a battery, so they can stay alone in remote areas, or obviously attach it to power and maybe internet connection. The first question that the client asked us in the past when we started monitoring of some structure was, yes, but this technology is valid, so it means it can be comparable with traditional ones. Well, here I'm presenting you a test that we did on a dam in Italy. And on this dam there is an area here where there is a landslide. And the client wanted to compare the results with a pendulum and a total station that were already installed on the dam. Here we see 2 points. No, it was just one, sorry. One installation point. This is the antenna positioned on the crowning of the dam. And on this dam we have the inverted pendulum. That's a very accurate and precise instrument, but needs to be built within the dam. It costs thousands of euros and provides just longitudinal and transversal measurements. And now we see the kind of accuracy that the total station can provide. Well, the total station in this case is positioned more or less 70 meters apart from the crowning of the dam. And exactly in the longitudinal direction, it works like a distanceometer, so it's the better condition for the station to work. And it has this kind of accuracy, so 0.3 millimeter longitudinal and 0.8 transversal. And it also provides information on the height of the point with an accuracy of 0.4 millimeters. So these are very good results. But you can immediately see that there are a lot of missing points. Well, here we have a dam positioned in the alpine area. We have a lot of days with heavy rain, snow, fog, and in those conditions, the total station cannot work and cannot provide information about the deformation of the dam. But if we look at the data processed with GNSS, low-cost GNSS for each stations, here we have a comparable value for transversal direction. Well, here the baseline, so the distance between the two receivers is more or less the same 70 meters. We have a worse longitudinal accuracy, but it's comparable. Let's say 1 millimeter, it's already a good result. And 1.7 millimeters for the up coordinate. But you can see that now you have a solution for all the days. So there are no missing epoch. And what happens if we go further from the total station? So these are two other points that are positioned on the landslide that have to be monitored because it's, remember you, it's on top of the dam. And now we have 1.4 kilometer of distance and more or less 570 meters of difference. Well, here I don't have the inverted pendulum, obviously, because I'm not more monitoring the dam. And these are the results of the total station. As you can see, now the quality of the data provided by the total station are a lot worse than before. So we have 5.5 millimeters in transversal directions, 6.3 in longitudinal, and the height coordinate is still very good. It's 6.9 millimeters. It's good also due to the fact that the total station now is working just to measuring the angle. So it's a point pretty far, pretty high, and it's measured the angle of for the movement of the point, and it has this kind of accuracy. If we look at the data from the GNSS, now the GNS outperformed the total station, especially in the transversal and longitudinal direction. And obviously here we have even more points where the total station cannot provide us results due to more distance and more troposphere, more clouds, or more fog. While even in this case, the GNSS solution is continuous. For the up, you can see that there is a correlation between the two measurements. So it means that the GNSS is measuring the same kind of deformation. But this kind of deformation can be actually improved by computing also the tropospheric effect. The client didn't want to do this because it wanted to compare the results with the total station that wasn't that were processed without taking into account the tropospheric effect due to the difference in height of the point. And this demonstrated that the system can actually work and can be compared or even outperform traditional method of monitoring. Here we see a different kind of installation on a bridge in Italy of Autostrada per l'Italia. And we have the following condition. We have a point, number 3, positioned on one side of the bridge that have been built on a bedrock, so it's stable. The other side of the bridge is on a landslide area. And we have, thank you. We have the point 1 that is on the pole of the other side of the bridge, while the point number 2 is freely can freely move. Here you can see a scheme. Basically, what we see is that these are actually real data. We see that we can detect a movement on the bridge of 6 millimeters that have been happening, And here you can see how in the daily solution or even in the hourly solution we can see the discrepancy of the position and find that there have been a movement and the bridge must be, well, in a certain way checked or be monitored because something is happening. Well, to improve the data, we have also to analyze other external sensors. So we try to include the information about just a normal temperature sensor. If we look at the green line, you can see clearly that the temperature is related with, especially with the longitudinal position of the point. And this is simple. Obviously, the bridge is dilating too with the temperature. So if we try to model the movement of the point without with taking into account the temperature, we can actually detect also very small movement. Like here, we have a movement of just 3 millimeters that were completely hidden by the other kind of analysis not based on an external sensor. So in principle, we are showing that we can also integrate the instrument with other external information to improve our solution and our modeling of the movement for the points. To conclude, I would like to state that the monitoring with single frequency low-cost receiver is possible. We have more than 100 points monitored constantly all over Italy. We have points in Japan and some in Holland. And the results have been validated and they have been demonstrated to be a valid support for management of the bridges or other structure. We have also verified that our station can resist to extreme weather conditions. We have a couple of points, for example, in the Alpine area, where there are more than 3 meters of snow. And in that condition, the instruments are continuously responding every day, every hour, and everything works fine. And that's all. I don't have a statement, but the statement could be that monitoring of a structure, especially considering that the structures are aging and sometimes are built on landslides, it's very important. Thank you.
Thank you.